problems. Okay, so roughly we had in the ternary Goldbach, we had the singular series. We did not talk about it, but in the book it shows you how you convert from a sum to a product. And we talked about how if you put an n as an even number, the singular series unfortunately vanished, which means the main term of the circle method is 0, which means you have absolutely no useful information after all that work. We'll assume we're plugging in an odd number. And then it turns out if the number is odd, the singular series is non-zero, and in fact you can bound it away from 0. That's extremely important. It's not enough for it to be non-zero. What if this was like 1 over n to the 2014? It's being multiplied by something of size n squared. Well, if this is of size 1 over n to the 2014, then this is going to become a negligible term, and it will be much smaller than the error terms. So what we need is 0 less than C1 less than sigma n. I'll put that it's less than sub C2. If it equaled plus infinity, that would not be bad for us. This is the important one, if n is odd. And because of something like this, we now have a chance of getting a theorem at the end of the day. There's a separation between the main term and the error term, so long as we can understand what's going on for the minor arcs. So the major arcs are contributing something of size n squared. Remember, we defined our function fn of x to be the sum p less than or equal to n of log p times e to the 2 pi I px. And so when you're looking at this, we've got these weighted sums, unfortunately, so we're going to have to play a little bit of log games. The number of terms we have is pi of n, which is about n over log n. The largest this function is going to be is if I take x equals 0, it's going to be of size roughly n. For other values, we expect there to be lots of cancellation. And we do not expect this function typically to be large. So the question is how large? Well, we looked at the integral from 0 to 1 of fn of x squared dx. And this is really nice. This was one of the key ideas, is that integrating the absolute value squared is very nice, because this is the same as integrating fn of x bar dx. But fn of x bar is the same of fn at negative x, the complex conjugate. And so what we get is we get the integral from 0 to 1, the sum over p1, the sum over p2, log p1, log p2, e to the 2 pi I p1 minus p2 x dx. And when we look at this, everything is finite. These primes are at most n. We can switch orders at our heart's content. The integral here is going to be 0 unless p1 equals p2. We'll get a sum of log squared. It's going to be about n log n. So when the dust settles, it should be about n log n. This is the average value of the squared, so the function itself should be roughly of size square root of n log n. Right? Another way of looking at this is if we try to use Cauchy-Schwarz to integrate the absolute value of fn. See, unlike the exam problem, this is a case where Cauchy-Schwarz will help us. So if we looked at the integral of fn of x just to the first power dx, this is less than or equal to the integral from 0 to 1 of 1 dx. Well, actually, it's 1 squared. And then integral from 0 to 1 of fn of x squared dx. So in terms of getting an upper bound, this is, Cauchy-Schwarz is very nice. Whenever you have a finite interval, you should think Cauchy-Schwarz. Whenever you have two functions that both converge, that are both integrable, or at least integrable when you square them, you should think Cauchy-Schwarz. This is harmless. In fact, it's really harmless because it equals 1. And so that's going to give you, the square root of the L2 norm. And so this is going to give us, fn of x, the average value will be of size square root of n log n. Okay? So now, let's try to see why the binary Goldbach problem is so difficult. So if we come back over here, fn of x has our sum like this, We got the stuff over here from the contribution of the major arcs. It was something of size n squared. I'm not going to worry too much about logarithms, although to make the matter work at the end of the day, you are going to have to worry about logarithms. I want to give you rough, big, broad brushstrokes. So major arc is roughly of size n squared. Let's see what the minor arcs give. So it's the integral over the minor arc. I'll just write it like that. And then we'll have fn of x cubed e to the negative n x dx. And we want to figure out how big is this. And the problem is the minor arcs is a very hard structured set. We have the absolute value of an integral. What's the most common thing to do? Move the absolute value inside the integral. Good idea or bad idea? Years ago, Saturday Night Live, when it was funny, had a commercial on bad idea genes on a group of people who just had lots and lots of bad ideas, and these were the genes for them. You know, one of them is talking about, you know, all the work they're doing on the place. They're ripping out the boards. They're putting in new appliances. You're renting, right? Yeah. Bad idea. This, if they were to do mathematics, this would be a wonderful thing. Why is this such a bad idea to put in the absolute value inside the integral?
We lose a lot of the cancellation.
Okay, be a little bit stronger than we lose a lot of.
We lose all cancellation.
Well, which cancellation do we lose? We lose the cancellation from here. We don't lose the cancellation from here. So if we put the absolute value inside, it's not the worst possible thing we could do. We lose this cancellation, but at least we still have the cancellation from fn of x. Really bad thing would then be go even further and put the absolute value inside there, at which point we'd be dead. So we at least still have some cancellation, but we no longer have any cancellation really over the interval, coming from the fact that this is going to be highly oscillatory when n is large. This is going up, down, up, down, up, down really quickly. If you have cosine, 2 pi nx, the period is 1 over n. It's moving up and down really fast. It should average things out. We've lost all of that.
Is this meant to be squared also? Does that move squared?
I don't think so. No, before we were just trying to calculate what's the average value of fn squared.
Oh, okay.
When we were doing the circle method, remember, we did this integral over all of 0, 1 tells us how many ways there are to represent n as a sum of 3 primes. So now we want to estimate this integral. One thing we could do is we could pull out the largest value over here and say the minors contribute less than or equal to the maximum over all x in the minor arcs of fn of x times the integral over the minor arcs of fn of x squared dx. Well, if you think about it, this is not so bad. The minor arcs are almost all of 0, 1. Now, the function is large on the major arcs, but the major arcs are very small in terms of length. Let's think about what's going on here. What size am I going to be getting for this integral here over the minor arcs? I'm sorry? At most n log n. It would be n log n if I integrated from all of 0 to 1. Well, I'm integrating over the minor arcs. If I extend this to 0, 1, I'm only making things larger. So this would be, the minors would be less than or equal to the maximum over x in the minor arcs of fn of x times the integral from 0 to 1 fn of x dx, and that's a square. So we've just extended the minor arcs to the entire thing, but only here. We've pulled out an fn of x first. This is the key step, is we've pulled that out first. Now we use this as at most, n log n, And so now we get less than or equal to the maximum x in the minor arcs of fn of x times n log n. And we're comparing this to some constant times n squared. It's got to be less than that if we're going to win. All right, well then that tells us exactly what we need for the maximum value. The maximum value better be constant n divided by a little bit more than log of n. So we need the maximum of x in the minor arcs of fn of x to be little o of n over log n. And that just means if you take the ratio of that to this, it's going to tend to 0. It's growing slower than big N over log n. Are you able to see or no? All right, so I'll rewrite it over here. So now, the question is, do you feel optimistic? So we need the maximum of x in the minor arcs. I'm sorry? Oh, this is what the major arcs gave constant times n squared. So if we're going to win, the only way we can win is if the minor arcs, contribute less. So we need fn of x on the minor arcs to be equal to little o of n over log n. What do you think?
Well, you can't use the naive. You can't use the naive estimate.
Can't use the naive estimate. Why can't we use the naive estimate?
It's n log n.
Not n log n, just gets to size n.
Well,
On major arcs, fn of x can be approximately of size n. So if we wanted an estimate like this to hold everywhere, is there any chance of this estimate holding everywhere? No. But how do we define the major arcs? The major arcs are all those points near rationals with small denominators. And near rationals with small denominators, we can approximate things well, and that's where we expect our function to be large. Typically, how large do we expect fn of x to be in absolute value? We expect it to be root n log n. All I need is a bound where I'm saving a little bit more than a logarithm. So there's a chance. So the typical size is square root of n log n. Only need to save a log of n to like the 1 plus epsilon. And that's how the proof is then completed. Is they then show that if you stay away from rationals with small denominators, that there is some cancellation they can get. So remember, we threw away a lot of cancellation from the e to the negative n. We did not throw away any cancellation from the definition of fn of x. We have a highly oscillatory sum here. And take advantage of that. So the rest of the proof is literally really rolling up your sleeves and doing a lot of technical calculations to get some cancellation here. If you think about it, and again, I am not trying to belittle anybody who has spent any time doing work on the minor arcs of the circle method. I've got to be careful because this is being recorded. It is extremely difficult. It is extremely hard work. But it's reasonable to expect that this can happen. The function typically is of size square root of n log n. We just need to save a log or two. Okay? In the greater scheme of things, this seems like it should be possible. Okay? So what I hope is that this is enough so that you get a sense of what are the key ideas of the proof of the circle method for the ternary Goldbach problem. We have completely skipped the minor arc calculations. It is using cancellations in fn of x, but the amount of cancellation we need is a reasonable amount. What do you think might help us get more and more cancellation when we look at these highly oscillatory sums over the primes? Yes?
Do we know that x is irrational? Because isn't the major arcs all rational parts, or no?
Well, remember, there's only countably many rationals. So the major arcs are the parts of 0, 1 that are close to a rational with small denominator. So the minor arcs, you have rational numbers in the minor arcs.
Yeah, just with big denominators.
Just with big denominators. What do you think might be useful in understanding these sums over primes?
How big is big? Oh,
What kind of hypothesis?
one of the generalized Riemann.
One of the generalized Riemann hypotheses. And if you look at the original paper of Hardy and Littlewood, which you were supposed to have done, I think they initially assume, versions of the Riemann hypothesis that there are no zeros with real part greater than 3/4. It's been a while since I've looked at it, but I'm pretty sure, is that what they assumed? And that's what they used to make progress. And it's a classic paper in the subject. And they relate this question to the Riemann hypothesis, or generalized Riemann hypotheses, understanding primes and progressions. You can begin to see why all of this stuff is connected now. We need to get some understanding of these sums. Okay, this was the ternary Goldbach. This was writing things as the sum of 3 primes. What should we do now?
4 primes.
No! No, 4 primes is too easy. 2 primes. It's like the something about Mary going from the 7-minute abs to the 6-minute abs. We want to do binary Goldbach. All right, so really this is horrible notation. I should really have put a 3 over here to tell us that it was coming from the ternary problem. I'll put a 2 over here now. If the only thing you care about is the ternary problem, there's no need to introduce another subscript. Keep things clean. But if you're now going from problem to problem, you want notation that you can look down and see. So now we have the binary Goldbach problem. And I think at the end of the day, the only thing that really changes is now I think you get something to the first power. All right, so now we still have these estimates as before. And now we want to do the exact same argument as before. And so now, we know the major arcs is roughly of size n. Okay? So the question is, what will we get for the minor arcs? So somehow for the minor arcs, doesn't want to turn. So somehow for the minor arcs, we need to get something less. We'll have the integral over the minor arcs of fn of x squared e to the negative nx dx. What do we do? Only thing we know how to do is move the absolute values inside. Are we happy about this? Yes?
Actually, no, that wouldn't help.
Yeah. Yeah, without knowing what you're thinking, almost surely it won't work. Lots of things have been tried over the years.
Yeah.
We move the absolute value inside. So now it's less than equal to the integral over the minor arcs of fn of x squared dx. Oh, hey, we know what that equals. What does it equal? Yeah. What does this equal? No! Sorry for those of you who are asleep.
Oh, well,
It's at most n log n, right? We don't know the integral over the minor arcs. We just know the integral over 0, 1. So one route is to then say, well, it's less than equal to the integral over 0, 1 of fn of x squared dx, which is approximately n log n. Oh, and our main term is of size n. Now, some things do help us. First, we're integrating over the minor arcs, not over all of 0, 1. And second, we've thrown the absolute value inside the integral. So just because this estimate is too large does not mean that binary Goldbach is false. It just means this line of argument has 0 chance of working. Okay? All right, so whoever's idea it was to put in the absolute values. Bad idea. Unfortunately, we don't have any better ideas. So we're going to still have to go with that. But it was a bad idea to integrate over all of 0, 1. What did we do last time? We didn't integrate the absolute value of fn cubed. What did we do? We pulled something out. Let's do that. And so this will be less than or equal to the maximum of x in the minor arc of fn of x times the integral over the minor arc of fn of x dx. So again, we're not integrating the function over all of 0, 1. Now, unfortunately, the difficulty is, how do we evaluate the integral over the minor arc? We could use Cauchy-Schwarz, which is what we did before, and relate this to the integral over the minor arcs of fn squared and take a square root. We could extend the integral to 0, 1. So if we use Cauchy-Schwarz, what do we get? We get the square root of n log n. Right? So we'll have this will give us like the integral of 1 squared, integral of fn squared 1/2. So this is of size square root of n log n. The whole thing is of size n. So we want n to be greater than the maximum of x in the minor arcs of fn of x times this. So this means the maximum of x in the minor arcs of fn of x, we want this to be much less than n divided by this, so that would be n to the 1/2 of a log of n to the 1/2, I think, if I've done my algebra correctly. Is everybody comfortable with this algebra? What's the average value? What was our bound for the average value of fn of x? Our bound for the average value was root n log n. This is less than our bound for the average value. Smaller than bound for average value. We need so much cancellation that its maximum value is less than its average value. It's not that bad because, remember, that was only a bound for the average value. But what we're seeing is that in order to make binary Goldbach work, we have to be able to exploit cancellation to such a degree that the worst possible x on the minor arc has more cancellation than our average bound of cancellation. Go home. We're stopping class. That's it.